This is the second lecture on the lecture series on optical properties of nanoscale semiconductors. In this lecture, I shall discuss about excitons and how these excitons controls the band gap of the semiconductor. So, first let us discuss what are excitons. In materials, the uppermost filled or partially filled band is known as the valence band, and the empty band next to valence band is conduction band. The forbidden energy gap between the conduction and the valence band is known as the band gap of the material. If sufficient energy, uh, which is greater than or equal to the band gap energy, is provided to the electrons, they may absorb this energy and jump to the conduction band. Thus, it leaves a hole in the valence band. This hole in the valence band and the electrons in the conduction band now form a pair due to electrostatic Coulombic attraction, because the electron is negatively charged and the hole is positively charged. So definitely there will be a Coulombic attraction. So such a neutral bound state of electron hole is known as excitons. Excitons exists both in insulators and semiconductors, and it also observed in some liquids. There are mainly four types of excitons: Wiener mode exciton, Frankel exciton, charge transfer exciton, and bi-exciton. This lecture will mainly describe about this first type, that means Wiener mode exciton, and its impact on the band gap of semiconductor nanomaterial. So, what is Wiener mode exciton? As we have already mentioned, this the in exciton, the electron and hole are bound together by Coulombic interaction, and we know the Coulombic interaction is q square by 4 pi epsilon r. So this Coulombic interaction is inversely proportional to the dielectric constant of the material. Now, if the material have very high dielectric constant, then the Coulombic attraction goes over 1 by epsilon. That means the Coulombic attraction is very low. As a result, these excitons is found to be loosely bound. So they may move roam around the lattice. So their excitonic Bohr radius may be extended to few unit cells, and thus they are delocalized. This type of delocalized exciton is known as Wiener mode excitons. To describe the dynamics of these excitons, effective mass approximation method is a very popular model, which mainly based on the nearly free electron model. In this model, the exciton is characterized by its wave vector k, and it is described by its Hamiltonian h equal to h cross square k square over twice me plus h cross square k square by twice mh and minus this Coulombic interaction term. Here this Me and Mh are the obviously the effective mass of the electrons and holes respectively, and this Re, this Re represents the mm, uh, position of these electrons and hole within the conduction band, and epsilon is obviously the dielectric constant. And this first term and second term basically the kinetic energy term of the electron and the hole respectively. This Hamiltonian, an observation shows that this Hamiltonian is almost identical with that of an hydrogen atom. So we can simply solve this Hamiltonian using the approach used in solving the hydrogen atom problem, and this is very trivial, and you can find the solution in any quantum mechanics book. So then we can find the excitonic binding energy. So this excitonic energy X is given by this expression, where this AB is the Bohr radius, excitonic Bohr radius, equal to 4 pi epsilon into h cross square m square. The not excitonic Bohr radius, the Bohr radius, originally what we have in the atom, and this M is, capital M is the effective mass of the electron hole system. And here we have mu, this mu equal to 1 by me plus 1 by mh is the effective mass of the electron hole system. The first term in this equation basically signifies the potential energy of this exciton system, and it is clear that the second term represents the kinetic energy associated with the excitons. In general, the second term is very small, and in most cases it is neglected. So, in case of exciton, the energy is represented by only this first term, that is the potential energy. So, the excitonic band gap of any semiconductor material, that is the band gap of the material in presence of this bound exciton, can be represented as this one, where we have taken the lowest state n equal to 1. Here this Eg is the band gap corresponding to the material when there is no exciton. So it clearly shows that in presence of the exciton, the band gap decreases because it contributes a negative term. However, uh, amongst the more popular semiconductors, zinc oxide is very popular to exhibit its excitonic effect at room temperature, because its exciton binding energy at room temperature is 60 milli electron volt, and it's quite stable at room temperature. However, for other semiconductors, this excitonic binding energy is less than the thermal energy at room temperature. So, excitons are unstable and not usually not observed. So, in this material, no band gap lowering is observed. It is also clear from this equation, if we go, it is also clear from this equation that this second term is the binding energy of the exciton, and it depends on the Bohr radius. Now, if we consider any nanoparticle which is size less than this Bohr radius, in that case the excitonic band gap can be represented by this equation. So this equation values under this condition that the radius of the nanoparticle is less than the Bohr radius. Hence, we see that this excitonic band gap strongly depends on this particle size. Considering this size effect on the excitonic band gap, we can write the general expression as Eg exciton equal to Eg bulk plus this Eq, which is due to the quantum confinement effect, and this last term is the term due to exciton. A more detailed calculation is also there, and it was done by uh, Brass, L.E. Brass, and the details of the calculation is can be available in this paper, where he has considered the fast excited state of the electron. This model is known as the Brass model. It shows that the band gap of any quantum dot is equal to its bulk band gap plus the term due to the quantum localization, that is the quantum confinement effect, and with a negative term which is due to the screen Coulombic interaction. We can show the variation of binding energy, excitonic binding energy with quantum dots through this graph, which clearly shows that as the size decreases, the excitonic energy gradually increases. Now, using some observed reported case, in case of serious quantum dots, we see that as the radius decreases, the band gap increases, and these circles are the experimental points, and this line is the theoretical fitted curve using this Brass model. And this is the result for this cadmium selenium quantum dots, and these two are for indium phosphide dots and cadmium tellurium dots. So we see that this model works. This Brass model agrees well with the size dependent band gap of quantum dots. So in the next lecture, I will be describing on the other three types of excitons. That means the Frankel exciton, charge transfer exciton, and the bi-exciton. So thank you very much.